Our next example is going to deal with the bomb calorimeter. Usually we use a coffee cup calorimeter or a laboratory calorimeter, but the molar enthalpy of fuels is calculated by burning the fuel in a bomb calorimeter. It's very rigid with a tightly sealed container which prevents the gases from escaping. By measuring the temperature change of the calorimeter and knowing the specific heats involved, molar enthalpy of combustion can be determined. The heat released by the combustion will be absorbed by the water and the calorimeter. So in this example, we have a calorimeter of steel with a mass of 322 grams filled with 225 grams of water. The original temperature of the water and the calorimeter is 10.6. When we have 1.02 of ethanol being burned, the temperature rises to 38.4 degrees Celsius. Calculate the molar enthalpy of combustion of ethanol, and it's giving us here the specific heat capacity of steel. So first, we need to determine the Q of water because we have the heat being released by the combustion will be absorbed by water, so that's our Q1, and by the calorimeter itself, Q2. So water is 225 grams. Its heat capacity is 4.184 joules per gram degrees Celsius, and the temperature change is from 38.4 to 10.6. So we need to subtract that, and we get 27.8 degrees Celsius. Our first Q is 26.2 kilojoules. Next, we're going to look at the calorimeter itself. So we have steel being 322 grams. That's our mass. Our heat capacity was given to us, 0.44 joules per gram degrees Celsius. It has the same change in heat. It's starting at 10.6, going to 38.4. The difference is 27.8. We get 3.9 kilojoules. To find our total Q, we need to add them together. 26.2 kilojoules plus 3.9 kilojoules gives us 30.1 kilojoules. Now, we need to determine the moles of ethanol. We know that we have a mass of 1.02 grams of ethanol, and we have a molar mass of 46.08 grams per 1 mole. Just grabbing my calculator, 1.02 divided by 46.08 is equal to 0.0221 moles. In our next step, we're going to find the delta H, the molar enthalpy. We're going to use negative Q divided by our moles. Negative 30.1 kilojoules divided by 0.0221 moles is equal to negative 1.36 times 10 to the power of 3 kilojoules per mole. And if we do a mental check, we know that combustion reactions usually release 1,000 kilojoules per mole of heat.